Over here we see the VP against VS graph for two transformers, and we are asked to determine which transformer is a step up, which transformer is a step down transformer. So this is the answer, and we can look at these values over here. This is the VP, which is 12 volts, and for transformer B, the output voltage is 24 volts. So 12 become 24. B is a step up transformer. And for transformer A, you see that the input voltage, primary voltage is 20 volts, and the output voltage is 12 volts. So 20 to 12, stepping down. Now, applying the transformer equation, we have transformer B. Vs and Vp can be obtained from the graph 12 and 24. 12 being the primary voltage. We can now plug in the number of turns of primary coil to be 200 to get 400 as the number of turns in the secondary coil. Now for transformer B, what is the current flowing in the primary coil over here, so that transformer B can power this lamp and operate the lamp at its normal rating. So the rating comes in very useful here. This means that we want the output voltage or the secondary voltage to be 12 volts. And if we see 12 volts secondary voltage, transformer B means that the input voltage needs to be 6 volts. So that's how you can get 6 volts as the primary voltage over here. Now, second thing is the lamp, when given 12 volts, needs to operate at a 10 watts power. So the power in the secondary coil needs to be 10 watts. Assuming a 100% efficient transformer, this means that the primary coil, the power is also 10 watts over here. So that's why we can plug in the 10 watts as the power in the primary coil. So with these two values known, we can then determine, using P equals IV, the current flowing in the primary coil to be 1.67 amperes. Now we are starting to work on a transformer that is not ideal. We can solve this in a similar way also. So first we will use the standard P power equals to power equation. Primary coil power equals to secondary coil power. But because now the transformer is not ideal, the secondary coil output power is only a fraction, which is 80% of the input primary coil power. So be very careful where you plug in this 80%. Always reason it out. The premise here is that the output power in the secondary coil must be lesser than the input power. So with this, we can then now use the power rating to solve, plug in the unknowns here. Same thing, the secondary voltage needs to be 12 volts to let the lamp light up normally. So secondary coil Vs to be 12 volts means that primary voltage Vp is 20. So we can plug in Vp is 20 here. Next, this 10 is the secondary power. Secondary power is over here, and we want 10 watts of power for the lamp. So that's why you can plug in 10 here, and that's why also we can determine the primary current to be 0.625 amperes. Now, transformers are usually highly efficient, talking about 90+% efficiency. It might not be 100% because of a few reasons. So there will be power loss and energy loss due to heat loss as current move in the coil. There's some heating effect due to the resistance of the coil. There's also some leakage of magnetic field lines from the primary coil to the secondary coil. The iron core is supposed to connect and concentrate the field lines over to the secondary coil, but there might be some magnetic field lines that escape. And lastly, there's this thing called eddy current, because in the iron core itself, the iron core is made of iron. It links the magnetic field lines over to the other side. But being made of iron, it means that current can flow inside the iron core. And this iron actually experiences change in magnetic field also. So the very reason why there's an induced current in the secondary coil applies to the iron core also. So the iron core will experience a little bit of internal current circulating within the iron core because of Faraday's law also. And we call this eddy current, and this saps away energy, resulting in energy loss.